and I'm gonna talk about the topic that I was recently interested in. So, out of all the topics, I was kinda into understanding each components of wav2vec 2 and how each of them work. And I felt simply like feeding enough samples weren't really a good enough explanation for me. So we'll start by my current mental model for the contrastive loss, and then we'll look into the transformer attentions, then the convolutional layers, and finally the quantizer module. So let's start with my UAI paper, and it's a bit mathematically dense, so I'll try to make it as minimal as possible. So the motivating mathematical observation is this. Let's start with the more common interpretation of the classification loss. We often learn that the cross-entropy loss as the maximum likelihood estimation, so it's basically maximizing the multiplication of py1x1, py2x2, and so on. And using the log makes the product as the summation, and py is modeled with the softmax function, which models the categorical distribution, so that's the usual explanation. But here's an interesting observation. The influency loss, which is the mutual information maximization loss, is equivalent to using the cross-entropy loss with the softmax function. So, in other words, classification loss becomes the mutual information maximization problem. And the same loss is also used in the contrastive learning, or in our turf, self-supervised learning. And it implies that it's also a mutual information maximization problem. So the summary is this. Supervised learning aims to predict the label y given the input x, and the training loss is equivalent, in fact, to maximizing the mutual information between x and y. And contrastive learning aims to maximize the distance between the similar samples, and it becomes equivalent to maximizing the mutual information between the anchor and the positive samples. Well, the anchor should be depicting the full input distribution, so it is in fact a combination of positive and negative samples, so I'm abusing notations quite a bit here, but hopefully the theory police here would spare me. And let's understand more concretely with an example, supervised contrastive learning, a new RIPS paper. Let's start with a batch of images with a batch size B and build a similarity matrix between each of the images. And out of all those pairs, the B squared pairs, the similar samples, or in other words, the anchor and the positive samples, is defined as the same class sample in this paper. Then maximizing the mutual information between x1 and x2 becomes equivalent to maximizing the mutual information between x and the label y, which is theoretically speaking equivalent to the original supervised learning classification setting. So we're basically skipping all of my theoretical contributions in the UAI paper, but anyways, let's move on. So let's consider the transformer component of wav2vec 2, especially on the attentions in this paper. The idea for the main experiment in this paper was, does the transformer attention really attend to useful locations? And to verify that, we need a short meaningful signal hidden inside a longer useless signal so that we can control the meaningful signal's locations and check whether the attention works or not. So I started with the speech noise dataset from AudioSet, like about 8-second noise, and a shorter signal, a 1-second signal, where we fine-tuned the wav2vec 2 based on the label of this meaningful signal. And we randomly positioned the signal within a much longer noise audio. So the resulting signal was in fact, like the transformer was in fact attending to that specific location. In other words, we only gave them the labels, but the model also taught us where those signals were, kind of like a weakly supervised scenario in the image side. So, well, we did not stop there. if the attentions were really that useful, why not use it in a knowledge distillation scenario? So we finished training the teacher model first, the wav2vec 2 model, and use its attentions to help the student model's training. So like using the teacher's attentions. And simply put, we are basically minimizing the distances between the student and the teacher's attentions. And it's like giving hints to the student model where to concentrate. And the better part here is that we only need student attentions during training and not at inference. So student model doesn't need to contain the attention mechanism inside it. So that means that we can also distill wav2vec 2 to CNNs or RNNs. So we checked the performance on two cases, FSD50K, which is a subset of audio set, a multi-label classification dataset, and the noisy speech commands v2, which is the dataset that I was talking about a few slides ago. And obviously, performance improves and more better. I couldn't write this in the paper because we were running out of time, but it seemed that it was speeding up the training as well, so that was super good. So the resulting attentions look very similar in the end, the students and the teachers' attentions, and now at last I can believe that the transformers are really attending to something, and their attentions really contains some useful stuff inside it. And maybe in hindsight it's kind of obvious, like transformer concentrates on useful locations, but anyways, that's it. And the third paper, which concentrates on the convolutional features only, and people usually freezes the convolutional layers when fine-tuning to the downstream task, but why? Like, people said like it would be behaving like a spectrogram, so don't mess it up, but okay, but is it really it? I checked the convolutional features, the raw features myself, the heat map things and everything, but it looked nothing like a spectrogram. So I wanted to check that, like what does those 1D convolutional layers do, and check whether the information that spectrogram contains is also inside the convolutional features. So it's temporal, frequency, and amplitude. And the most simplest spectrogram friendly approach would be using the sum of few sine signals and observe their manifold. So I had to check how much temporal detail does the convolutional have. It's stacking of 1D convolutions, so the CNN in the end has about the window size of 25 millisecond and the stride size of 20 millisecond. So the structural limit should be around there, and within the 200 Hz signal, I sneaked inside the 800 Hz signal inside it and draw each stepwise features manifold using the UMAP. And it seems that the features were indeed capturing that temporal detail, surprisingly. Let's move on to the single sine signal case to check the fundamental frequency. So if we draw it, like using UMAP, the left figure, it is kind of curvy, but anyways, neighboring signals have indeed similar F0, like a Q. So no wonder the wav2vec 2 representations clusters speech signals based on gender information. The right figure is we directly measured the distances between the neighboring convolutional features, and surprise, surprise, the distances were nearly identical, unlike what we usually use, like Mel or Bark. Apparently the model doesn't really care whether it's low or high frequency. And I extended this further into formants, where I see the first and the second harmonics, which is really critical for vowels. And the left one, the left two figures, is if we fix the fundamental frequency F0 and vary F1 and F2. And the right third and fourth figure is we vary F0 and F1 and F2 all together. So let's see the left one first. And the manifold is surprisingly built in a locally rectilinear way, so like the formant information is stored inside a relative manner, inside a local grid structure, locally. And also I'm kind of skipping the linguistic details like the corner vowels and everything, but I also compare the original wav2vec 2 and the XLSR, which is the cross-lingual trained version of it. And that training really does make a difference. And let's see the right two figures. And XLSR uses, to my knowledge, stuff like YouTube, so that the data is not speech only, and then there are lots of noise inside it, unlike the original wav2vec 2 model, which uses the audiobook data. So the original model has only heard the male and female, clean male and female voice, so the representation seems to be comes quite close with each other, like the male ones and the female ones, unlike the left one, the right one, the XLS-R. Finally, the amplitude. It's also similar to the one before, the formants. The amplitude information stored inside the local grid structure. So the conclusion is, till now, it sounds like we went through quite a hassle to show that the convolutional features were equivalent to that of the spectrogram. But that wasn't what we wanted to show in the end. CNN stores information in a relative manner, and spectrogram stores in an absolute manner. And what that means is that let's consider a simple sine signal, which with a fundamental frequency of 100, 200, and 8 kilohertz signals. If we measure the distances of the spectrograms, all three will be more or less equal with each other. But for the learned features, 100 and 200 hertz signals will be much more closer than that of 8 kilohertz signal. So the final component of wav2vec 2, the quantizer. Basically, vector quantization is clustering real space vectors into a few centroids, so that one can think this like translating a real value vector into an integer, something reminiscent of a tokenizer in NLP. And wav2vec 2 learns the codebook, each of the clusters, during self-supervision. And my hypothesis was that it would be clustering acoustically similar signals, so that we can utilize them in temporally summarizing the signals. So let me be a bit more clear. Thanks to the quantizers, we can now identify which neighboring audio frames are similar, right? This implies that we can simply cancel out the duplicate ones, or in other words, identify which region is redundant and which region is important. Vowels are much more longer than consonants, but we usually use simple average pooling when we use the final representation, which implies that we are giving them all of them the same weight with respect to time, but this method doesn't. And so the key thing here is that we don't need supervision on the downstream task when temporally summarizing the representations. In fact, this is quite an explored problem in the NLP domain, so we had to import them as our baseline. But anyways, ours were quite good in about 4 tasks. So there's AP is average pooling, SP is statistics pooling, which is quite used in the speech side, and the whitening is quite common in the NLP side, and ours, VQLP. And by simply changing the polling, the representations are far much better clustered with each other. So the recap here is that contrastive loss is in fact maximizing the mutual information, transformers are attending to useful locations, and CNN was storing temporal frequency amplitude information in a relative manner. And finally, quantizers were clustering acoustically similar signals. So I'll end my presentation with my potential future work. Is wav2vec 2 really a phoning collection dictionary thing? And the CNN side, how does the model capture consonants and how can we experiment those? Because vowels are relatively easier because we can get to see the formants, but consonants not so much. And also on the quantizer side, I'm curious how each centroid would sound. So the current codebooks was somewhat inefficient because it only uses up to 20-something%. And I already tried to reconstruct the signals to no avail. And anyways, Finally, the phoneme recognition problem. I tried using wav2vec 2 for phoneme recognition, but the performance is weirdly low. If I train only with the CTC loss, the word error rate seems okay and it's reproducible, the original colophone paper. But if I train with a stepwise classification loss, the last year's interspeech method, the accuracy is in fact quite bad, and I have no idea why. And thank you for listening to my presentation.